In 7.1d, we're going to determine if a statistic is considered to be an unbiased estimator of the population parameter. So we first need to define what is an unbiased estimator. And what it is if you look at the mean of a sampling distribution statistic. So for example, on the last slides, we looked at a sampling distribution of medians. So we had all these dots on the distribution that represented median. If I take the average of all of those medians, so take the mean of all of the statistics in that distribution. Now, if the mean of the statistic actually equals the true value of the population parameter being estimated, it's considered to be unbiased. So we thought for the CHIPS that the true population parameter is 50%. Well, if we take the mean of all of our medians and it was close to 50%, that means the median is considered to be an unbiased estimator. Another element with that, an unbiased estimator, in repeated samples, it estimates won't consistently be too high or too low. So what we're going to see to be unbiased, if we do more and more samples, it's really going to start to even out to what it should be. Another point, almost always it's not equal to the value of the population parameter. We're just taking many samples. So if we only take 100 samples and we average it out, it's not going to represent the true population, but it's going to be close to it. But it may not equal it exactly, and that's okay as long as it's close. The last element, when choosing between estimators, we want to figure out what type of estimator best represents our population. So should we look at the mean, the median? The one you want to actually ultimately choose is the one that has the lowest variability in it, or the spread. So let's reference the one simulation you did about the deck of cards. Remember, we went in and we shuffled the deck of cards and we picked 5 cards and we computed the median from that. Was that considered an unbiased estimator of our population of cards? Well, the true median of the deck of cards, if you put the cards in order, what the median is of the true population is the card number 6. So that's the median of our deck of cards. This is assuming we only use the cards 2 through 10, by the way. So we're going to get rid of the face cards and the aces. So if we do a simulation of 5 cards and record the median, here's what a sampling distribution could look like. And you're going to notice what I did is I did M hats. This right here, this number 3, that dot was the median of one sample. This here is a median of another sample, and so forth. So we took many samples from the deck of cards, which was our population, and recorded the median. Well, let's take the mean of all of these medians and see what we get. If you do that, I get 6.2. So do we feel like using the median as a calculation is a good representation for this deck of cards? Absolutely. This is not exact, but it's very close. So in this case, we would consider the median of our deck of cards of choosing 5 cards would be an unbiased estimator. Well, if that's unbiased, what's a biased estimator? So in a biased estimator, by definition, is the mean of the sampling distribution doesn't equal or even come close to the true value of the population parameter. Fine. What might be a good example in this case? Well, let's look here at a population distribution. This is the population of heights of various individuals. And here they're looking at the actual mean this time. So the mean height, or the mu, of the population is 66.07 inches. The range, by the way, is 21 inches from 54 to 75. So these are actual population parameters. Now, what if we do a sampling distribution? You're going to notice here they are taking a sample size of 4, and they're going to compute the mean. So they're going to go to the population, randomly pick 4 individuals, compute the mean, and plot it. Here they did this many times. They took many samples of size 4. Well, what is the average of these means? The average is 65.67. So looking at that, if we just compare, how do we feel about this calculation? That feels like it's pretty much an unbiased estimator, and I would say it definitely is. Okay, let's switch gears. Let's also now take a sample size of 4, from our population and record the range, because that was the other calculation. If we record our various range outcomes, here is the sampling distribution. Now, take the mean of all of those various range answers, and you're going to get 10.12. Now, is 10.12 fairly close and related to the population range of 21? Absolutely not. In this case, it's very far off. Therefore, using range as an estimator for this particular population would be considered a biased estimator. I want to talk through this activity my brick and mortar class had done because it's a nice example of, is this considered biased or unbiased? So here, each student wrote his or her name on a piece of paper and put the number of hours of sleep that they tend to have. I then took all of those cards with their names on it, mixed them up thoroughly, and took a sample size of 4. So here we're looking at N was 4. And recorded the hours of sleep for the 4 randomly selected students. And what we did is we recorded the IQR and we recorded the maximum for those in terms of each sample size of 4. And then we're going to make an actual sampling distribution of what the results were for IQR and maximum. So we'll work on that sampling distribution. Now, what was the true answer? I'm going to tell you for this class, the true answer for IQR was 3 hours of sleep, and for the maximum was actually 12 if I looked at all of the cards that the students had submitted. So these are the population parameters. We're going to compare the population parameters for each of these compared to the mean of the sampling distribution of IQR and the mean of the sampling distribution of maximums to see which one of these elements here or statistics is considered unbiased versus biased. So ultimately, here was the data that we had. Again, we have our true population parameters here, and we have all of the raw data here. Now, what I want us to do is to take a sample size of 4, and we will record the IQR and the maximum for that particular sample. And then let's go ahead and do this sample many times to create a possible sampling distribution. So what I did back in my brick and mortar is I had 23 students, so I had each one of them do one sample of size 4. And they recorded IQR and max. These were the results. So this is the IQR and here was the max. Now keep in mind the population's IQR was actually 3. And then the population's max was 12. So when we come on in here, if we add these up and take the average of the 23, what you're going to find here is that the IQR actually ended up being for the sampling distribution about 2.4. And then the maximum, if we take the mean of all these maximums, the average was 8.4. So based on that, I should determine, are any of these unbiased estimators, are any of them biased? If we look at this and compare these here, if we had to pick, clearly this would be our unbiased estimator, whereas maximum would be our biased estimator. We can conclude, because the approximate sampling distribution of a sample IQR seems centered near the number 3, it appears that the sample IQR might be an unbiased estimator of the actual true IQR. However, because of the sample of the approximate sampling distribution of the sample max is much lower than the true value, which is actually at 12, the sample maximum is a biased estimator of the true maximum. The sample maximum is consistently lower than the true maximum. So let's wrap up with this, sampling of heights. Suppose the heights of adult males are approximately normally distributed with the mean of 70 inches and the standard deviation of 3. To see why sample size matters, they took 1,000 SRSs of size 100 and then they calculated the mean heights. They then took 1,000 SRSs of the size 1,500 and calculated the sample heights, sample mean heights. Here are the results of the graphs so you can see. So this was a sample size of 100, 1,000 times, and here's a sample size of 1,500, 1,000 times. clearly you're going to see that as the sample size gets larger, that the distribution of the sample mean was less variable. Clearly this has less spread, which is the same thing as less variability. So in other words, when the sample size is larger, the sample mean will be closer to the true mean on average.